In this tutorial we're going to look at conducting factorial ANOVA. So factorial ANOVA is a generalization of the forms of ANOVA we were looking at previously in terms of a between groups design, where instead of just having one independent variable or one thing that's being manipulated, we have two things that are being manipulated. So in this case we're looking at a study which is described in the tutorial notes, where a researcher is interested in looking at the effect of alcohol dosage on driver reaction times. Now, for this exercise, what I want you to do is extend on what you did last time, which is enter the data. And to do that, first of all, we just need a little reminder of what the data looks like. So we have here, the first column represents, in the between subject study, the data for each person. Alright, so you can see here, each row represents one person's data, and column 1 tells me which person is being compared. Okay, so we can see here that we've got a data set set up, and in fact this data set is set up as a between groups comparison. Okay, what we can see here is that each row of data represents one person, and each column represents a variable. The first variable we can see here, the one that's labeled subject, is a participant ID. It tells us which person the data has been collected from. So person 1, we can see the next column we have a variable called gender, and this tells us that the person is male. Now you might be thinking I've typed the word male in here, so just a reminder from last week, what we've done is we've got a labeling device turned on. The labeling device is value labels. If I turn that off for a moment, you can see that what I entered to get a gender of male was a 0. Okay, down here where I've got a female participant, we've entered the value of 1. If I turn the value labels back on, clearly the data set's much more readable, but it sometimes hides the underlying data that's actually doing the job of being analysed by SPSS. Effectively, SPSS really knows only how to analyse numerical data. There's some limited string handling capabilities, but we need to set up our data with a data structure in mind that's based on recording either fixed integer values to represent categories of things, or continuous variables, and they typically represent the measured outcome. So in this case, our latency variable is an outcome variable. So it's what we would call a dependent variable. Its score is dependent upon the treatment group or condition that the participants are participating in. So what this first line can be read as is participant 1 was a male who had no alcohol or a drink that was not alcoholic, which may have the participant may have believed to be alcoholic, and the latency of their response, in this case this was a simulated driving task where the participants were asked to respond to a red light by pressing a brake pedal as quickly as possible. Their latency to respond to that red light was 207 milliseconds. Okay, person 2 was male, they also had the placebo, and their latency to respond to the red light was 216 milliseconds. You see here we've got the 207.09 milliseconds. If we have a millisecond accurate timer, which we do in this instance, then the only certainty we have in this measurement is up to the millisecond level. This 0.09 is what we call false precision. It's the computer generates these numbers, but the computer is inaccurate beyond 1 millisecond. So in fact, these numbers are meaningless. What we might do is go to the variable view mode and change the number of decimal precision here in latency so that it's actually 0. Now, this actually doesn't do anything in terms of analysis, but it reminds us that what our true level of accuracy is. And it's really important to keep in mind when we're talking about doing statistical analysis that we have this true level of accuracy. It's silly to claim that things are more accurate than they actually are. Right, once the data is entered, what we can do is just put any labels on that we need to make the output more readable, and also that will help us later on when we come back to investigate the data again if we put the study aside for a couple of months or something. So here you can see that we have the columns on the variable view page. First one is the name of the variable. This is a short name. Technically it used to be only 8 characters long, and obviously you can't say very much in 8 characters, which are restricted to letters, no spaces and numbers. So it might be that, you know, it's very easy to know what the meaning of gender is, but if we have the DAS21 for example, and we have DASS1 and DASS2, if we haven't looked at the DAS for a long time, we won't know the meaning of the DAS1 or DAS2. So what we want to do is we actually want to put a long meaningful label associated with that variable. We can do that here in the column marked label. We can put in up to 255 characters here that says exactly what this is. So if we just click on this, as I've done, double click, then we can say participants gender, and then because that's reasonably clear, we know that we're now talking about participants gender. We've got part of the job done, but unless we specify a value with it, later on we could come back and not be able to remember if 0 represents male or 1 represents male, or we've got 2 representing male or something like that. What we need to do is associate a number with each category. Let's say well at the moment you can see we've already got male set up as a 0 and 1 set up as a female. Let's say we have some missing data and we wanted to analyze them separately, so we might put in value 2 and type in missing. Okay. This provides us with a way of analyzing the contribution of those people whose gender is unknown. In fact, missing is sort of confusing here because we deal with missing data in a different way altogether, and in this case we're actually including those people in the analysis. Normally if we don't have data on someone, we want to exclude them from the analysis. So rather than calling this missing, let's go up here and change this to undeclared. So it may be that this represents someone who responded on everything else but didn't want to declare their gender. So if we click on change, we now have 3 categories here. Okay. Now if we were to go back to the original data set, you can see if I've got a 0 here, I have male. If I've got a 1 here, I have female. And if I've got 2 here, I've got undeclared. Let's fix this up. Go back to 0, and the other thing I'm going to do is I'm going to take my undeclared away because I don't want to mess up my data set. Alright, so we're now ready to run the analysis. We've got meaningful labels on the output, which is going to help us interpret the output. To actually run a factorial ANOVA, we go once again to the Analyze menu, click on the Analyze menu, General Linear Model. Now because this is 2 factors, we don't want to do compare means for a single factor. We go to General Linear Model Univariate. Okay. From here we put our dependent variable. Dependent variable is the thing that's being measured, so it's latency for the task. And fixed factors, and these are the things that were manipulated in the study. The participant's gender, okay, that's a naturally varying, but for the purpose of this analysis we're going to treat it as a fixed factor because it's a quasi-experimental design, and the amount of alcohol consumed. Okay, so both of these are between subjects variables. We now go to the model, full factorial. Again, full factorial includes the interaction, so we have gender and group being the factors and covariates, and the interaction term being included, and the sums of squares are type 3, indicating that this is an experimental analysis. We go continue. Contrast, there's only 2 groups, so there's no point doing contrast. Plots, always useful to have. So what we want to do here is have any categorical variables typically as separate lines, and any continuous variables on the horizontal axis. Okay, in this case, the horizontal axis, the thing which is most continuous, if you like, or which represents a step series, or at least an ordinal series, is the group, because we have 0, low concentration, high concentration. Placebo is 0 dose. So we'll put that in the horizontal axis, and then we'll have separate lines for the genders, for males and females. We can add. Sometimes what I'll do is I'll include this in both orientations, because it'll be easier for me to see what's going on. But really just a single plot is sufficient here. Post hocs, because this is a 2x3 design, there is some value in doing post hocs. If there's an effect for gender, we know that males are different from females. If there's an effect for alcohol, we know that there's been some difference by dosage, but we don't know if the difference is between the placebo and the low, placebo and high, and so forth. So we go to post hoc. Actually, we only need to put the group in. And again, I'm going to choose Tukey as a mid-range. Least significant difference doesn't provide adequate protection from type 1 error. Tukey provides moderate levels of protection. Sheffe provides lots of protection, but makes the test too conservative, and it's a bit like throwing the baby out with the bathwater in some instances. So we'll go continue. And my options, I want to look at descriptors for everything here. I want the effect size and power, and I also like to check my assumptions. I can check some of these other things as well, but for the moment we're just going to do this. Go continue. Once again, I can click paste to make a log of what I'm doing, but in this case I'm going to go straight to OK. Here's the syntax that's been printed out. Now that's been printed out because of an option that I put in my log file settings. Alright. What we can see, again, looking at first of all the between subjects factors, is a specification of the design. We can see here that we have two levels of gender, 0 and 1, that's male and female. See, putting the value labels in makes it clearer to work out what a 0 is and what a 1 is. We've got 30 in each of those groups, and we've got the amount of alcohol consumed. 0, placebo, 1, low concentration, 1.5 standard drinks, 2, high concentration, 3 standard drinks. And we've got 20, 20 and 20, so we've got a balanced design there. Okay. It's also usually worthwhile looking at this stage at the means and standard deviations before we begin to see if there's any out of range values. All of these means look like they're in an acceptable range for response latencies, so we suspect that the data is probably good at this point. We can see the standard deviations vary a bit, okay, which might indicate there's an underlying problem. If we look at the Levine's test here, we can see that the Levine's test is suggesting that the sample variance is not equivalent in each cell of the design. So that means we should interpret the result with caution. Probably don't get too excited about this, but it is something to keep in our mind. It means if the effect here was at, say, the 0.05 level, it was marginal, rather than concluding there was a difference, we might want to set a more stringent alpha level, say 0.01. Okay? But looking at this, we see that in fact we have F values which are high and P values which are quite low. Typically, since an interaction invalidates the main effects, I look at the interaction first, and this seems to be generally acceptable practice. So the gender by group interaction, that is there a different effect of group depending on your gender? We find F with 2 and 54 degrees of freedom equals 11.46. P is less than 0.001. So there is a significant gender by group interaction. Okay, and that accounts for partial eta squared 0.30 rounding up of variance. And the observed power there is in excess of Cohen's 0.8, it's 0.99, so it looks like a highly reliable result. So we would report that, then we would look at whether or not there was effective gender by itself. Actually, gender collapsing across all groups is really what we should be saying. And we can see gender collapsing across or ignoring all groups. The statistic is F with 1 and 54 degrees of freedom equals 29.34, comma P equals 0.001. Looks like there's a gender effect. And again, eta squared is good, power is good. Group, we can see F with 2 and 54 degrees of freedom equals 330.69. P is less than 0.001. The effect size is large and the observed power is high, indicating that it's reliable. A fully crossed interaction is going to make those main effects unreliable. So at this point what we really should be doing is looking at a way of looking at the post hoc analysis. And strictly speaking, what that means we need to do is split the results down within groups. Okay, so we should look at the effect for males separately from the effect for females, and then look at the effect of dose. But just to have a quick eyeball at the data, what we can see here is looking at the gender effect first. The dotted line here is the female data. You can see that the female latencies are longer than the male latencies. This is consistent with what the literature says. Body mass has an impact on how well you absorb alcohol. If you have more body mass, you can absorb more alcohol without affecting your performance. Females typically have less body mass than males and consequently are more affected by alcohol earlier at lower dose rates. So in other words, we would expect to see this lengthening of response latency in females more than in males, and that's exactly what this plot shows. If we then go up to ask the question, has there been an effective dose? Now this is again collapsing over both males and females, so saying ignoring whether or not you're a male or a female. The Tukey test here says group 1, this is the placebo, is significantly different from group 2 and from group 3. So they're each in a separate column. So this is placebo and it's by itself. The subset 2, the low concentration, is by itself. It's significantly different from both group 1 and group 3 at the 0.05 level. So alpha equals 0.05 here. And finally, high concentration, 3 standard drinks, is significantly longer than both 2 and 1. Now, because of that interaction, what we really need to do is redo the analysis of dosage effect within gender. How do we do that? The easiest way is to go up here to data, okay, go split file, and what we're going to do is organize the output by groups. So we're going to organize the output by groups on gender, go OK. Then we'll go back to our analysis. Now we can't analyze gender any longer in the factorial design for the simple reason that we're now looking at what is the effect within males and within females. So we can't say how many females are males or how many males are females. So we have to take this fixed factor out. And so what we're doing now is we're redoing the analysis for males and females separately, looking at the effective amount of alcohol on latency. Right? We no longer have a plot of gender because gender's not in there. So the only thing we can do is put in our horizontal axis group. Okay, continue. We once again, we could do contrast, and in fact let's do a contrast just for the sake of it, because you can think about these as being 1.5 units apart, 1.5 standard drinks apart in the 3 conditions. We can see whether or not there's a linear trend. So if I ask for a polynomial here, this polynomial will look to see whether or not there's a linear trend in the data. That is, whether or not your latency varies continuously, monotonically with the dosage of alcohol that you consume. Post-hocs, again, group, we can do the Tukey test, go continue, and options. Now, to some extent, technically we don't need to do both a contrast and a post-hoc because they're both effectively telling us the same thing. However, oftentimes, such as in repeated measures designs, post-hocs are not available, but contrasts are. So it's worthwhile knowing how to be able to do both sorts of post-test comparisons, contrasts and post-hocs. Okay, so we'll go OK. Once again, we have the output looking at much as it did previously. You can see this time though, the first set of output is labelled participants' gender equals male, we can see that we've got 10 males in the placebo group, 10 in the low concentration group, 10 in the high concentration group. Okay, we can see here that we have the means and standard deviations for each group. We can see that there is a variation in the variance between each of these groups. The low concentration group has the smallest standard deviation of all three groups, so we need to treat our main results with a little bit of caution. When we look at the main effective group, we find that for males the effect of dosage on performance is high. F with 2 and 27 degrees of freedom equals 154.03. Significance is less than 0.001. Partial eta squared is 0.92 and power equals 1. So this looks like a reliable effect. The fact that there's a mild amount of violation of the assumption of homogeneity of covariance is not a concern here. This is a very robust result, which is not going to change on the basis of that small violation. If we look at the cheeky results, once again what we see is that each group is different from the next group. So you can see we've got a significant difference between the placebo, low concentration. On average, the response latency of the placebo group is 212 milliseconds, of the low concentration group 231 milliseconds, and the high concentration group 259 milliseconds. It looks like this on the plot, but once again there's vertical exaggeration here. So personally I like to make sure that the scale on the graph is set with a true zero, and we set a meaningful upper limit. Actually, let's go for something a little bit lower. And you can see here that the effect is not as dramatic as it first appeared, but it's still clear and self-evident that there's an effect of alcohol on response time latency. So following the male data, we have data for females. Okay, and we can see here again the design tells us that the analysis was correct. You can see there's actually comparable standard deviations in all three groups here, so there's no violation of Levine's test. If we look at the effective group, it's actually a little bit larger than the male group. So F is 181 with 2 and 27 degrees of freedom. The effect size is 0.93 powers 1, so it's reliable. If we look at the post hoc results, again we can see there's an individual difference between each of the three groups, and that is also evident in the chart. If we just fix the scaling, we should see some evidence of a slightly more pronounced slope, but it's going to be subtle, so we're not going to be overwhelmed with this, I wouldn't think. Just get that scale correct. Okay, to the eyeball it's not strongly evident, but we can see some evidence of a more pronounced slope than was evident for the males. Okay, I mentioned before doing a linear contrast or polynomial contrast. If we go back up here a little bit on the output, okay, we can see this table, contrast results. Okay, the contrast results here, linear represents a straight line relationship, quadratic represents a curvy line, exponential growth or growth curve. Okay, so here we can see the linear, here's our contrast estimate, This is the hypothesized value. The difference between the two values tells us whether or not there's a significant linear component, and we evaluate it with a p-value, significance here, 0.000. So what this tells us is that the relationship between the three means is linear. A straight line can be adequately fitted to those 3 points: placebo, low concentration, high concentration. Obviously there's no point doing this with anything less than 3 points, okay, because any 2 points will always have a straight line between them. 3 points, we're getting a fairer test. The quadratic, we've got 3 points, and what this is telling us, because it's not significant, is that the line described is a straight line, not a curved line. Okay, so this is telling us that amount of performance impairment associated with alcohol is a linear relationship. There's a direct linear relationship between the amount you drink and how slow you are to respond, at least for this data set.